this conversation could go on for a while, but we do have to stop. So I would like to thank you again, Joshua, for a really fun talk and being part of the workshop. Next, we are going to now move to a panel discussion on where and how knowledge representation can benefit machine learning and what should be explored. I have the pleasure of introducing the moderator of the panel, Rao Kambhampati. He's a professor of computer science at Arizona State University. His work deals with planning and decision making, and it's motivated by the challenges of human-aware AI systems. His work has been recognized by numerous awards. Among other things, he's a fellow of AAAI, AAAS, and a bunch of other things. He's also served as the president of AAAI, I think 2016 or 17-ish. And he's a trustee of HCI. I think really I'm fairly certain you don't want to hear me talking, so I'm going to hand it over to Rao, who will introduce our panelists whom you've met before through the day, and take it away, Rao.
Okay, so you can hear me, right?
Yes.
Well, let's get started. For those of you, basically, so that we're having this panel on why, when, and how to leverage knowledge representation and reasoning for machine learning. For the younger researchers in the audience, it's probably worth remembering that this panel, as well as this title, would have been almost redundant and unnecessary as little as a few years back. Knowledge representation focused on representations for knowledge that we have, whether they are logical or probabilistic, and machine learning focused on learning descriptions of the world in terms of those representations. Much of this, of course, has, however, looked at what have been called explicit knowledge tasks. I mean, the KR and AI originally looked at those explicit knowledge tasks, things that we not only do, but we know how we do it. We have very good knowledge about them, so we could give this to the machines. And the tacit knowledge tasks, such as the vision and motor skills, and significant part of language processing remain mostly out of touch. Things, of course, changed quite a bit recently, and we made tremendous progress in these tacit knowledge tasks. AI has really become synonymous with vision, language, and motor skills right now, and much of this has been thanks to deep learning. Interestingly, that has sort of created a bit of a cleaving between the idea of representing knowledge and learning. And thus, of course, this panel, just when really they should have come together to combine explicit and tacit knowledge tasks, it sort of became as if they were two very different ideas. In fact, Jeff Hinton, whose ability to turn a mean turn of phrase rivals only that of Oren Etzioni, as far as I know, has gone as far as to identify AI approaches that take any kind of explicit knowledge as input as intelligent design approaches. I mean, what scientists worth their salt would like to be identified at all with intelligent design, right? We are no bunch of creationists, right? Of course, as many of the talks in this excellent workshop, including 4 by our invited panelists here, would have convinced you, explicit and learned knowledge shouldn't be on the warring paths at all. It is as futile to look for knowledge from humans and tacit knowledge tasks as it is to spurn their knowledge that they're ready to give you unexplicit knowledge ones. Now, of course, how to do this right is the topic of our panel. We have 4 panelists who have all not just talked about it, but worked on these specific tasks about how to combine learned knowledge and explicit knowledge. Oren Etzioni from AI2, and Heng Ji from University of Illinois, Urbana-Champaign, Victoria Lin from SalesForce, and Jiajun Wu from Stanford. There's no question that these are all illustrious folks. They're so illustrious that we actually invited them to give talks in this workshop. So rather than give additional introduction to them, I want to dive right in. We have 3 minutes statements from each panelist to talk broadly about their work and how KRR and ML can be combined. This could be sort of an approximate summary of their talk, but hopefully also broader than beyond their work. Followed by, we will have some question between the panelists. And I also note that the panelists, having heard their talks, are largely sympathetic and are on similar wavelength, at least to me. And so to keep things lively, I will play loyal opposition and channel Jeff Hinton and Rich Sutton in the best way possible. Imagine them wearing a kurta and trying to yell at you. So we'll do that, and let's get started. Who would like to go first? First 3-minute statement. Oren, you?
Can you hear me okay?
Yes.
I found your remarks so thoughtful that I was watching it double, but then when I started talking, there was a feedback loop. I'll say something very brief, because I think that these things are a lot more fun when they're interactive, and I don't want to repeat my talk. Somebody missed it or forgot it since the morning. It's basically a practical way on top of transformers to build McCarthy's old vision of an advice taker. And it uses language and neural representation as the underlying representation. So it's one way to try and put together explicit knowledge, KRR type of ideas, and implicit knowledge of the kind we find in a transformer model. I'm sure there's lots of other ways. But Rao, you were raising the question, should we even bother, right? I do, I think, to say it in one line, thought is not a vector, right? Unlike Jeff Hinton's statement. Think about it, right? Even a very long vector, it's just hard that all of humanity, all of human cognition, which is what we call thought, boils down to a vector of weights. It just doesn't seem very plausible. And another technology that is very appealing nowadays is, end-to-end differentiable systems, gradient descent. And we've seen those technologies do wonderful things, particularly at scale. More wonderful things that we would have imagined 2 years ago. Go and GPT-3, right? There's no question about that. But again, let's do a thought experiment and ask, is human intelligence end-to-end differentiable? And to help with that, let me just suggest the following simple thought experiment. Think about the Windows operating system, or maybe even just the kernel. Forget about all the device drivers for printers and other things. That's a pretty complex system. And I think most of us would agree it is not end-to-end differentiable. We would not want to learn it from scratch. We would not want to learn it purely from examples, as per Rao's ideas about having innate knowledge and not reinventing the wheel from examples, right? Okay, so I think most of us would agree about the Windows operating system. So now the question is, what's more complex? What's more baroque? What's more sophisticated? The kernel of the Windows operating system or human intelligence? And again, I think most people would agree that there's more to human intelligence than the kernel of an operating system. So I'm trying to use this thought experiment to break us out of this kind of mindset of, oh, it's all just neurons hopping around and updating their weights. I think there's more to it than that. And what that more is, I'll leave to my co-panelists, and I'll stop there.
Victoria, would you like to go next?
Thanks, Rao. I think ever since I've been started interested in machine learning, so I'm fascinated by basically jointly statistical learning combined with structured data. I think probably one intuition is that as humans, we don't just do pattern recognition all the time. So it seems that it's natural, a truly intelligent system should have some ability to rationalize built into it. So that's why I found structured data like programs, knowledge graphs, or databases are natural test beds for this type of thinking. Especially myself recently, I'm focusing on question answering over relational database, it has great practical value. And also relational database data models have lots of interesting structures. But I also like reflecting on my work, I just realized actually since I started working on this problem, I didn't play with a lot of neurosymbolic data myself, algorithms myself. So like what I presented this morning, so we tried transformers on translating natural language questions to SQL queries, and it worked pretty competitively on benchmark data sets. So, and also thinking about like the industry environment, like I'm currently in, so there is a trend that data augmentation or like sometimes training with auxiliary tasks is very popular technique. So partially because they are very easy to apply, and partially because a lot of times they can be very effective. So like reminds me of recently we had one work called grammar augmented pre-training for table semantic parsing, where we try to make sure the question and the database schema are more tightly grounded to each other. So instead of adding links to explicitly model this type of grounding, we synthesized artificial data, and then we try to make the model to predict auxiliary labels based on these type of artificial data, so that like implicitly it learns this type of grounding better. So that's one trend I noticed in my work. And also like another thing I was thinking regarding, so why it seems that a lot of times we encounter obstacles applying symbolic modeling to some real world tasks. So one thing I thought is still grounded to the text to SQL problem. I felt like a lot of times maybe it's very hard for us to design or like pre-coded the symbolic knowledge, and it is well known. And I think like I would like to extend that maybe the part we can code ended up being the easy part. So what I mean is like, for example, we want to translate natural language to SQL query. We know database has the schema structure. We know SQL has the program structure, but maybe this part doesn't deal with the core difficulty of the problem, which is basically we want to map natural language to the program structure. Just knowing the program structure space doesn't help a lot. So, and also like, yeah. So finally, I just mentioned like, so a lot of times I found like linguistic compositionality actually help the task more than the compositionality on the symbolic data set. That's what I have.
Thank you. Jiajun?
Hi. Yeah, I'm Jiajun. I work more on actually less on, not really on natural language, but I work more on like computer vision.
There's nothing wrong with that. I think computer vision is great.
Senior understanding systems, and then it has been especially in like in vision or speech, but in vision now more like people see like deep learning has been so popular and powerful, and indeed they solve a lot of recognition problems. But on the other hand, you can still see the limitations, especially in terms of generalization. In terms of you have to require a lot of annotated data for learning, and it's mostly focused on recognition problems, not on understanding other aspects of the scene, such as like object geometry, the physics, and how humans may interact with the scenes. So this is like my the theme of my research, and then in my research I think about if there's a way that we can integrate like these learning systems with some level of modeling of the world. But then, as Rao just said, right, there's all those debates on whatever you put in, maybe it will hurt your system, because it seems like whenever you have a large data, it's always best to learn from the data. But I think my argument here would be it would be good to think about what is the, not to put in too much, but to think about what is the minimal structure, but also the most universal structure that we can borrow and integrate into any of these scene understanding systems. So what are these minimal or universal structures? I would say to understand the physical world is to build or find out the minimal physical model of the world. This in computer vision includes, for example, how scene or how image is formed, right? The 3D and 2D projections, that all those things that we use in computer graphics. And also all those things we use in physical simulation, right? How the object had physical interactions, and if any of these knowledge about object from graphics, from physics can be built into C understanding systems, as well as the human level, hard level structural priors that we building when we actually make all those man-made artifacts. You know, the nature is very diverse and maybe not as regular, but when we make all those artifacts like chairs or monitors, then there is a human prior there, and then we made it to be symmetric. We made it to have repetitive parts. So if it's possible to integrate these kind of more like symbolic program-like structure into, for example, a 3D reconstruction C understanding systems. But this is like, I would say the main philosophical motivation behind my research. Yeah, that's it. Thank you.
Heng Ji?
Yeah, so I firmly believe that we need both symbolic semantic knowledge and distributional semantic. These two directions are complementary. And we have found the power of combining them together in all kinds of frameworks in NLP applications. So symbolic semantic representation, usually they are more explainable, they are more effective when you want to order them, compose them, and basically they're easier to manipulate. And since the NLP community has been working on building all kinds of linguistic resources, knowledge bases for 6 decades, right? So we should not just throw them away. We should try to figure out a good way to use them in modern methods. And distributional semantics, they are easier to extend to multimedia, multilingual setting, and they provide a continuous representation rather than discrete. So you can capture uncertainty, you can do soft decisions and soft matching. So they are basically much more generalizable than symbolic representations. So in my talk, I actually gave 5 very concrete solutions about how to integrate them together. So the first 2 are about encodings. So the first one is basically you can manipulate your data directly. For example, if you find, like Victoria talked about tables, right? Tables are fundamentally different from sequences. So you can encode some special things in the table, interdependency among the rows, the positions, and how the facts are interdependent on each other. So you do data manipulation directly in the first step. Or you can combine some external knowledge, like what you talked about in his knowledge graph work. You can encode the knowledge graph embedding together, combine that together with our, sequential embedding in a graph neural network. So we can have the power of both the symbolic representation from external knowledge and the input local content. And then we also did a lot of work on take advantage of a symbolic representation, such as semantic parsing, to control the decoding. So you can learn global constraints, global features, and you can narrow down your search scope when you do your application. And then finally, I think a lot of other work has been really trying to do a more superficial way of combination. You let distributional semantics take care of classification, and then you use some symbolic knowledge to do the reasoning, which is also okay. But usually, if you can kind of incorporate the symbolic knowledge in the earlier stage, you will see better gains. And the other very interesting direction I think people didn't explore a lot is about how can we use distributional semantics to do clustering to discover new knowledge. For example, how can we discover new types of events? How can we compose the event schema, right? Like Joshua just talked about that in his, how can we discover these laws and schemas automatically? But then when we presented them to users, we need to make them human understandable. So in that phase, then we can use symbolic knowledge to give a naming for each of the new clusters we discover. So that's my statement.
Okay, great. Thanks. So as I have a couple of questions to get us started off, and I'll sort of pose each of them to some of you, and then we can then go beyond that. So the first thing, I guess, is I think Oren already kind of mentioned this in terms of what are the compelling reasons. He gave a deeper reason, perhaps, but I think in your own talks that I've noticed, you have mentioned, of course, efficiency and accuracy as sometimes the reasons why you might consider combining explicit and learned knowledge. was wondering, are there other kinds? I think Heng Ji kind of pointed out explainability to the users. And I'm just curious in your own work, whether you've seen other reasons as to compelling reasons for not doing end-to-end and actually taking explicit knowledge. It could be explainability, interpretability, worries about biases in the kinds of inferences the system might make. I was just curious if any of you have anything to say on that aspect as to, I mean, it could be from your own work or things that would like to go. Shall I name names? So, Oren, you have something to say?
I think it's all those reasons.
All those
and
reasons.
Again, I think you're getting a silence. I haven't been a professor for some 6 years now, but I still remember. I tried to teach an interactive class the way, Rao, you're trying to obviously have an interactive panel discussion, and so I would ask the class a question. And those of you who may be junior professors, you could take some notes now. And often it would work well, right? We'd have a good discussion, but sometimes the question would fall like a lead balloon. Nobody would answer it, no matter what I did. And after 25 years, I realized that this happens in two cases for me, as other cases. One is when the question is too hard. You just ask her, hey, why don't we can one of the panelists just give us the blueprint for artificial intelligence in 25 words or less? You get stunned silence. The other
Actually, no, the previous panel was, talked about for 45 minutes, but go ahead.
Okay, but fair enough. They're smarter maybe than mine. The other one is when the question is too easy. So I feel like we all know that the technology as it stands, right, suffers from all the things that you mentioned, the bias and the.
I'm curious as to whether you specifically found that. I mean, I know in general that can happen, but was any of the things other than accuracy and efficiency being the driver for your own interest in using explicit knowledge? Basically, you could do end-to-end versus take explicit knowledge, whether that might, these are probably the possible reasons. But let's go forward. So the other thing that I was sort of curious about, I guess maybe we can talk more on, I guess what is the sort of the broad approaches that seem to be working for combining explicit and learned knowledge. In particular, these days, learned knowledge has become essentially, I guess, for tacit tasks at least, deep learning. So I was wondering, I guess, I mean, there are, especially in addition to the things that you've already tried, such as I think Oren talked about giving natural language rules and then make the system sort of deal with them. Are there other specific kinds that you find people don't actually spend as much time working with them, and they should, perhaps?
I can go next.
Okay.
So I think both Oren and I worked a lot on scientific papers, and what we found, compared to news domain, these sentences and the papers are written in a very domain-specific way. It means that the authors, they express some terms, abbreviations just for experts, right? So if we just use bird embedding or any variants of a bird embedding, look at the local sentences, the model won't be able to understand those abbreviations and those concepts. So I think one domain that one direction we should really explore more is how can we encode the external knowledge. So it's like when you are not understanding the content in the paper, you will refer to some external ontologies or dictionaries. But how can we organize the knowledge, right, from those external knowledge bases ontologies? In different domains, they have different structures. Like a bio domain, you can see a very deep hierarchy of these concepts, and you can also see a very detailed definitions. So what will be the most effective way to combine that external knowledge with what you can see in the text itself. I think that that is a very promising direction. And then also coming back to what Oren just said, I feel like it's not just about efficiency. Sometimes this kind of symbolic knowledge can really improve the quality, because for example, when we are looking at some implicit attributes, like what you mean by happy and sad, right? Like, so if you ask a kid to draw a picture about a family, they usually put things like butterfly or grassland, happy faces together. This kind of things, I mean, it's very different when what we are doing normally looking at the local context. So yeah, that's what I want to say.
Anybody else wants to weigh in? So I have kind of a follow-on with respect to that. And by the way, you can also bring up thoughts that that you think we should talk about. That would be great too. So a follow-on would be that, I guess sort of channeling the inner Jeff Hinton. Basically, the one idea people have, the closest many deep learning people have sort of come to the conclusion is that they wouldn't mind having some inductive biases, except oftentimes these inductive biases tend to mean network architectures. And one of the things that, of course, the panel here has looked at is a lot more explicit knowledge than just explicit, like network architectures. For example, just having heard your talks, I know that you have looked at rules and norms, and you have also looked at shared vocabulary, for which you then learn the denotation in the case of Jiajun. Some others have looked at causal models. So would you think that actually it would be possible to learn that meta knowledge too? And there's an advantage in doing that. I mean, I'm sort of channeling the opposition view that, why take anything if you can learn it yourself? And so the question then would be, would you think that the kinds of knowledge that you were using in your work could have been sort of learned if over a longer period of time, perhaps? And if so, would that cause any additional headaches?
Yeah, just to break the silence, I'm not a junior faculty anymore, but I taught my class for the whole semester, online class. Let me just briefly comment on that. I would highly recommend Jiajun's recent work on event knowledge, using to show how events connect to each other. So she built a very smart, very big corpus in a very smart way. So I think data-driven methods need to be used instead of traditional, hand craft knowledge. That's one thing, because only if you use the real data, the model can learn from those examples and can match a real scenario. And my recent work on event schema induction is highly inspired from her work. So we are trying to use similar ideas, looking into historical data, a lot of large-scale news, because history repeats itself. So we are hoping that we can capture those kind of causality, interdependency among the events, and so that when you see the new scenario, you can do prediction.
Anyone else?
Maybe I can point to Jiajun, because Jiajun is really the only junior faculty here.
I think it's the inductive biases in the architecture is of course very interesting, but also I guess it's there are other things that it's really related to, for example, in computer vision, there's recently I think there's a lot of interest in using position encoding, which has been quite popular in NLP, I think, although I'm not an expert there. But now I think people are finding different ways of parameterizing the basis in computer vision, instead of maybe just like sequential. People realize that sinusoidal basis or representations as positional encodings will really significantly improve the performance of many like reconstruction or view synthesis problems. Right? So that's kind of very interesting, because this is really not like well, is that a change to our network architecture, or is that change to the input, or so it's kind of like a gray area here, and and also I think there is a biases that you can build in, not in terms of architecture, but in terms of learning mechanism, right? They're just like a wake sleep algorithm, which in some sense is interesting in the sense that there are different phases, and while you can learn from data, you can learn from your past experiences, which may come later in the stage to actually change the way you represent knowledge in the systems yourself, or learning not only to learn from data, the representations, but also learning ways that the representations can restructure and build on top of themselves. So I feel like these kind of learning mechanism, in addition to the input data, in addition to organized input data and the inductive biases already in the network architecture, to me, I feel like these are all very valuable.
Okay. Anyone else? Okay, so there is actually a question on the Rocket chat, but I'll get there. But I have this other thing I want to ask. So I was kind of curious because three of you are sort of in natural language processing, and Jiajun is looked at vision. So NLP is this strange thing where it is sort of between tacit and explicit. Vision, at least the lower level vision, nobody questions. It is actually very much tacit, but then you somehow seem to be able to combine that with, explicit knowledge. So I was curious whether there would be differences in the kind of approaches that one would try in combining explicit and learned knowledge, depending on the types of these tasks. I mean, we have at least two big tasks. One is, language, which has this advantage that everything is in language, and then the vision part. So do you have any general thoughts on that?
I think, it's true that language seems to me like at a higher level of abstraction, because every word, is created by humans. So you created that for a reason. It's already at a different level of abstraction compared with pixels. But on the other hand, in vision, I think it's true that it might be hard to connect that to or more knowledge representations, but that's only the case if you care about semantics, because I think when the vision problems that are most common or most familiar to people might be like recognition, whether it's a chair or a table. And in that sense, that seems to be okay, not that much structure there. But if you look at other computer vision problems, like especially like those, for example, like 3D understanding or scene reconstruction, and there's a kind of a very rich set of structure knowledge, but not in the sense of like it's not coming from humans. It's not we made it ourselves. Like okay, DC is the capital of the United States, but it's come from the nature in the sense that okay, every image, right? Why this pixel become the way it is? It's because there's a 3D structure, there's perspective projection, there's how light transport works, and there's reflectance, and these are the actual properties that now we understand it quite a bit. We can write down as physical equations, and that's why the graphics engines and animation movies are so fantastic, and they're knowledge or explicit knowledge in a different form. So I think it's definitely also, to me, very valuable to think about how this can be integrated with learning. And it's true that in computer vision, actually these days, and graphics as well, there's a trend on making this knowledge differentiable so that they can be easily integrated with the learning system for inference, for recognition, or for reconstruction. So I feel some kind of hybrid representations or models are definitely valuable, although indeed the form of the knowledge, explicit knowledge, might be quite different if you look at vision applications and if you look at language applications.
That's why we need a multimedia common representation, right?
Multi-modal representation. I think you talked a lot about that actually in your talk. Yeah.
So I'm always jealous of computer vision people because you can find the focus of image and video much more efficiently than us. I mean, we usually need to have a deep understanding of the whole article and then understand what's the topic. But usually when you look at the painting, you immediately know it's about a flower and what kind of environment. And if you look at the video, two people are saying goodbye in train station, then you automatically ignore the background like trees. And so something is going on in the cognition, make it much more efficient than natural language. But I think natural language can make things more nameable. Like, when we were working with Professor Xibu Chang in Colombia about the event representation for videos and images, sometimes we have no idea how to use bounding boxes to represent events. Like two people are meeting, should we mark their faces as a trigger, or should we mark the shaking hands as a trigger, right? So it's not like a phrase or word we normally see in natural language. So that's why we need to collaborate. We should focus more on multimodal representation.
So did you want to say something, Oren?
I just want to add a small point. I very much agree. And there is this mega trend, of course, exemplified by your work of multimodal. A while back, we created this testbed called Iconery, which is basically a version of the game Pictionary. We used icons and so on, and it's available at iconery.allenandI.org. And I just encourage you to play with it, because we are continuing to do research and to open it up. And Pictionary is a great game where pictures and phrases come together. So the semantics, on the one hand, isn't that complex, right? It's not Shakespeare, but on the other hand, it's very much a multimodal. And again, it's a whole nother talk what we're finding there, but I just encourage you to have a look and email me if you want to collaborate on this project.
Victoria, did you have something?
So I personally didn't work on a lot of language and vision, joint language vision problems. So I do work on a kind of interesting images. So it's basically plots. So so like we have people ask questions, and like the target would be to generate some images, but like in the form of plots. But like there, the problem is slightly different in the sense that the plots are still defined in programs. So like you have a very concrete space of like what the plots could be, and like there, like the inductive bias is defined by the plotting program space.
Okay. So something that Jiajun said sort of made me think of this point, that the knowledge that is not learned, that's coming from outside, may be something that humans know, versus it's just some regularity in the nature that somehow is a higher level knowledge than what might be learned in the beginning. So I think this sort of connects to, I also noticed that there's a lot more interest in talking about system 1 and system 2. And saying that everything is system 1 until now, and one of these days we're going to do system 2, and then there would be a lot of happiness. I was curious as to whether any of you view the system 1, system 2 aspect and knowledge representation and ML combination aspects to be the same, or there are important differences. I think obviously there's at least one difference that Jiajun mentioned, I think. So that's, to the extent explicit knowledge is something that you're asking humans, there is regularities in the nature that you don't have to ask. But I'm wondering whether other things, whether there's a way to think of this in such a way that the system 1, system 2 distinction is the same as what we are talking about. Oren?
Oh dear. When I was a professor, I hesitated to call on people. The thing that I was mulling over as you were saying that is whether that system 1, system 2 distinction, which is of course a brilliant distinction, but it's one that's made about people, whether that's really even applicable to the kinds of systems that we're building, right? Because the thing that strikes me more than anything, whether it's a deliberative process or whether it's kind of an instinctual, rapid thing, is that we're dealing with very narrow slices, right? And even if it's multimodal, it's still a very narrow slice. And humans almost inevitably are dealing with a much broader set of tasks and confluence of tasks and so on. So I guess my answer to this question is, I just don't think that we are ready to talk about our systems in terms of system 1, system too, until we build non-savants, right? I like to call ourselves AI savants. And this is tied to all this, leaderboard, and then it fails on other leaderboards. And so we're working on transfer learning, but the transfer learning is often transferring from one thing to another thing that looks, very similar to it, right? Nobody says, oh, I transfer from playing chess to warfare, or transfer from, writing poetry to building better relationships, right? It's so I guess my answer is a non-answer, but I'm still with this. We need to build far more sophisticated systems to have this conversation.
Okay, so there's one question that Tom Dietrich asked that I want to channel to you. So he says, Jiajun's comments raise an issue. In physics and chemistry, we are seeing lots of work on creating differentiable prior knowledge, but not in NLP. Why are we seeing this discrepancy between these two worlds?
Yeah, that's actually very interesting. Yeah. Also, this relates to Raul, one of your earlier questions. What are some of the broader approaches that can make this fusion happen? Well, I think in physics, yes, in chemistry, in physical simulation, there are all those work on trying to make those large-scale simulations differentiable. In computer graphics, there's all those efforts on making graphics rendering differentiable. And then they can be integrated with any other like state estimation networks, or in graphics that would be like computer vision systems. And yeah, why is that not in NLP? I don't know. I will leave that to the NLP experts. But I feel like maybe I can say, why people are doing that in physics or in chemistry or in graphics is, in some sense, I feel like these are the areas that we already have good knowledge of the domain, and then we can write down, in many cases, what are the actual equations that governing these interactions of the molecules, or how light travels. And because we can write it down, then we are able to make approximations, first order approximations, to make things that are differentiable, and to make approximations even when there are points of discontinuity. So maybe language is like a more abstract reasoning process. So there's no written rules about how we reason and how we parse language, and maybe that's why it's harder. But I don't know. I think I'll leave the NLP part to the NLP experts here. Yeah.
I actually want to push back the question a little bit. I don't think we are not doing enough work on using prior knowledge, and there's tons of work. I think Oren's earlier work using background knowledge for.
No, I think
the question is not about not using prior knowledge. It's about how to create differentiable prior knowledge. How to make them differentiable.
In fact, another take on that, Jiajun, maybe that all you know about vision and graphics is essentially something that basically the civilization learned, these mathematical models, and so they are already differentiable to begin with. But lots and lots of things, like the kinds of rules that that we might have, the norms, societal norms we might have, they're not necessarily in the mathematically differentiable format. So the only thing, there's nothing natural about vision models. It is probably to you, but not certainly to me. But whereas natural language is a lot more natural for most of us, so we have to then consider going into the differentiable aspect. So actually, we are coming on the end. So I have one question, but you can either answer that or bring up whatever else you want to say before we end, which is, are there times when you do not want to input knowledge? So are there practical reasons for inputting knowledge, even when it can be potentially learned from the corpora, natural language corpus or something? And at the same time, are there places where we shouldn't put explicit knowledge, since it's all mostly made up and people don't know what they're talking about? So that's like one thing that we can talk about. Or anything else, your final thoughts? We'll just go once around. And let's go with Victoria first this time.
So maybe I will follow up on the differentiable knowledge in NLP category. So I think it is indeed, it's not just NLP, it's just like if you talk about logical reasoning systems, things becomes non-differentiable. So I think one category, a branch of work I know probably is like, so somehow bring in reinforcement learning. So like, although like we don't have a differentiable goal you can compute, but sometimes like you can have human define rewards for the particular type of inference or whatever you do. So like reinforcement learning can be a way to introduce such kind of feedback into NLP systems.
Okay.
Just sorry to interrupt. I just want to make sure, Heng Ji, you were starting to say something, and then we jumped into this. I just want to make sure that you had a chance to finish your thought.
No, I think I misunderstood I didn't hear the differentiable part, the modifier. Now I'm checking the chat, and now I can see the question.
Just wanted to make sure.
Yeah.
Well, so while I've interrupted,
okay,
my summary is that I think that we should be a little bit careful of the chauvinism of the data. And what I mean by that is I'm an empiricist like everybody else, and I love the idea that we collect enormous amounts of data, whether it's from cameras, from the web, and we use that to build the systems. But we do have to remember, and of course that ties into the bias issues that Rob mentioned earlier, and to a lot of issues that we're seeing nowadays in these systems, garbage in, garbage out. And there's a lot of garbage out there. So we are building systems, if we are purely empiricist, we are building systems that incorporate a tremendous amount of garbage, and now we've got a problem. So even this ideal that some people have, right? We should be completely learning from data. It should be questioned. Is that really the ideal?
okay.
I stop there.
Okay. Jiajun?
Yeah, I think it's is that like the closing remark, or is that responding to
Whichever way. You get one shot.
No, I think it's to me I feel this discussion very helpful, because it also reminds me, especially also Tom's question about like different forms of knowledge, right? And should they be encoded in the same way, or should they be like different ways of encoding them? And yeah, if they're like very heterogeneous forms of knowledge, and how can we, especially if we care about, as Oren mentioned, right? If we want to build multimodal AI systems, then how to integrate these kind of structured knowledge while they may originally be present in very different forms? I think that's kind of a very interesting question. It seems to be or something that was further study, and that reminds me of make me think maybe some of my future research can be related to that.
That's what panels are for. Heng.
Yeah, I just want to follow up on what Oren said. I completely agree. We need to be extremely careful when we collect the data before feeding into the model for learning knowledge. So we need to do very careful curation before and after the model learns knowledge. So recently we are working on misinformation detection, and you need to basically collect a lot of true information. So what does that mean, right? For different topics, and for a lot of unknown things, right? About, for example, vaccine. What is true, what is false. So we need to do very careful curation and collect a diverse source, not just working on English, working on multilingual, local news sources, pay attention to them. And after we collect the knowledge, we need to do very careful curation as well before we deliver that into our downstream machine learning applications.
Okay, great. Thank you all for your comments and thoughts. I just think that this is, to me, this was very interesting. I hope it is interesting to you and the people hearing. It's possible that we are not as flighty as solving the entire world's AI problems. You guys seem to be suffering from the humility of actually having solved a small piece of it to go off on high flights. But I think that's exactly what I was hoping we will get out of this panel. And thank you again, and have a great rest of the day. Thank you.
Thank you so much.
Thank you.
Are we live? Okay. All right. That was really a fun panel. Thank you so much to all the panelists and also to the moderator, Rao. We now come to the end of this edition of the KR2ML workshop. It has been a really exciting exchange of ideas, and we really hope it will continue beyond just the workshop. If you're interested in helping organize future editions of this workshop, either at NeurIPS or at other venues, please get in touch with us, and we can do something about that. All that's left for me now is to just thank people. I want to thank all our speakers, the panelists, the contributors, the participants, everyone on Rocket Chat for this excellent program. And especially thanks also to the workshop co-chairs and support team from Slides Live and Gather Town, without whom things could not have happened. So thanks to everyone, and I hope to see you all at a future venue. And that brings us to the end.